textbooks manufacturers and publishers like to they like to change things up every year to pretend like they're giving you something new, but in actual fact, it's the same stuff. And all of this is based on Isaac Newton's work, which was done hundreds of years ago. So it's not like it's brand new things, yeah. Nice, yeah, Takai. Take a look at it, mate. It's good looking. So this is chapter 1, and really is, I can't remember how many slides, but there's only it's only 7 or 8 slides. So I've added some little question things at the back, and it's very basic. It really sets us up for the rest of the course. And although it's only a few slides, it's really important in here, guys, that we're going to form some good habits for mechanics, statics, and dynamics for that matter, moving forward. Now, remember, this course is primarily concerned with statics. So when we're talking about statics, we're talking about things that are stationary or things which are moving, but are moving at constant velocity. Therefore, there's zero acceleration. So just remember that and be mindful of that. I think there is another course in dynamics. I'm not sure whether this course covers dynamics. I don't think it does. But there is, I think, a separate dynamics course as well. Okay, so just remember that we're trying to extract some very important principles out of this. So this is what we're going to be covering in today's lecture. So what is mechanics? Systems of units, and that'll be my first introduction for you into Excel. Very basic. It's nothing, I mean, you guys might be already well aware of this. I don't care. I'm going to teach it to you anyway, because I'm going to treat you like you know nothing. Yeah. And then we got method of solving problems, which I think is really important, especially when you move into more difficult problems. You could be tempted to think that, oh, I no longer need to stick to my strategy for solving problems. Okay. And I think it's also very handy for exam scenarios. A lot of you just kind of, everything goes out the window, and you kind of forget yourselves when you're doing exams. And this is the time where you need to go back to your habits, and you need to start forming good habits early on. A lot of you have left high school and you've learned some habits. Some of them are good, some of them are really bad, and you need to break those habits and start off something new. And then I think the last topic is numerical accuracy. So this is what we hope to cover. We're going to cover this today. And at the end of this hour, we'll be done, and then we can answer some questions. Yeah. Okay, so mechanics is the study of bodies under action of forces. Fancy way of saying I've got a body and I've got gravity acting on it minimum. If I've got gravity acting it on minimum, if I don't have anything supporting it, what's going to happen? It's going to fall. It's going to fall. It's going to start accelerating. Typically, what we're talking about here is bodies at rest or at constant velocity. So remember, bodies at rest, you're going to have a reaction force acting vertically. So this is where I get to, sorry, I'm going to stop sharing that, and I get to test my magic marker here. And you guys are the ones I'm experimenting on. So here I have a body. Stop making fun of me. I can see you guys are making fun of me already. The only ones I can see on the chat here on the right are Nicole, Josefa, Calvin, and SN. And I know you guys are laughing at me already. So stop it. Okay, so I've got a body. That body has mass, M, okay? And it's acted on by gravity, which is 9.81 meters per second squared, yeah? And that acts straight down, vertically down. Okay, I'm just using this as a reference frame. And typically I have an X axis and I have a positive Y axis. And this is how I usually define my axes whenever I'm drawing a free body. There we go. This is my first free body diagram that I'm showing for you. Even me, an engineer of 21 years, work at Boeing, we do free body diagrams all the time, okay? Now this typically is not the thing that we're analyzing in mechanics of solids, or what we're doing here in MM103, because this body is accelerating. So what we usually do is, okay, it's accelerating down, therefore we have a surface. Okay, so we've got a surface. Now this is no longer a free body. Okay, I've got to, let me just erase that. And I don't care that I'm covering something that we're going to cover later on. Okay, eventually we're going to cover free body diagrams in detail, but if I just keep on integrating it into everything we talk about, I think you'll understand that free bodies plays a very important role in your life as an engineer. So this is no longer a free body, because why? I've got a surface in there. Okay, so now what I have is a real situation, and because that body is at rest, if I don't react it with a force, this body should pass straight through this surface. So now I'm acknowledging that that surface is playing a role in this system, and I have a reaction force. So here I have an applied force equal to M times G, right, which is equal to mass times gravity, which will have units of newtons. Okay, up here I've got a reaction force acting vertically up, and that will be equal to, I don't know. Okay, but let me be clear, this is not a free body yet. The free body occurs when the body is not suspended by any sort of real interference. Yeah, so for it to become a free body, I need to remove that surface. Now this body is basically suspended in space. It's not accelerating down in the negative y direction, and it's not accelerating up in the positive y direction. It is essentially held stationary by the applied force of gravity and by the reaction force, which in this case are going to be equal, because what I do know is I have one equilibrium equation, which is positive vertically, sum of the forces in the y direction equals 0, equals R, which is acting positively in the y direction, minus F. Therefore, the reaction force R is equal to F, which is equal to mg. This is the kind of thing we're studying. Okay, sorry, I can see some questions coming up in the chat. A work of art. Thanks, guys. I really appreciate that, Akura. Adhura, sorry. I thought it was a Japanese name for a second, like Akira, you know. Thanks, Dwayne. All good. No, the session is not being recorded, unfortunately. Sorry, because I don't think the ITS person is here. But like I said, I'm not doing anything super complicated. Like I said yesterday, like I said just a little while ago, David, what if the ITS person doesn't show up? I won't give a lecture tomorrow. Okay, we'll switch everything to next week. Hopefully, they'll have the recording situation sorted out, and then we can start with chapter 2 next week. Is that okay? I didn't want to waste today. Yeah. Sorry, I'm just looking through the questions. Any questions here? Oh, Rohan, you just came in now and you're asking if I can recap. What's going on, Rohan? Don't give yourself away, mate. Just pretend like you've been here for the last 11 minutes. I haven't really done too much, Rohan. I've just drawn this pretty picture, and that's about it. And I've gone through the summary. But please turn up on time. I'm going to be here on time. If you turn up on time, we're going to get along well. Otherwise, I'm going to have to rewind everything for every person that comes on late. Yeah. So again, the reason I'm drawing this is we're just covering what I was talking about, which was our first topic of what is mechanics, right? Which is, in this case, we're looking at bodies which are at rest or are in constant velocity. Now, this is a body at rest. Before it was accelerating due to gravity, but then I put a surface in its place, and it hit the ground basically, and there was a reaction force R. So that's the only reason that I'm drawing this. Now I'll just go back to the notes. Can you guys see what I'm seeing again?
Yes, sir.
Yes, sir.
Great. So
Yes.
so then typically that's what we're going to be doing, guys. We're looking at statics. We're not looking at accelerating bodies, dynamics in the traditional sense of it. Now, typically we are looking at deformable bodies in the sense of small deformations, okay? So deformable bodies in the sense of small. Oh no, sorry, I'm just pressing the wrong thing here. Stop. Stop. I pressed the wrong button. Sorry, I'm getting used to this. I'm getting used to this pen. Okay. Deformable, small deformations. Okay. So we're looking at small deformations. Now, what am I talking about in the sense of micrometers or fractions of a millimeter? So that's typically the kind of deformations. And you're going, oh, you know, when you're talking about deformable bodies, is that really a deformable body? Yeah, it is. Okay, so materials can change due to thermal stress. It can due to mechanical stress or strain. So temperature, heat, and also pressure and load, right? So how big those deformations are, and we call them elastic bodies at the end of the day, because we can, in typical elastic region, we can apply a load, release that load, and it will return to its original shape, okay? So it is a deformable body, but not in what you guys would consider a macro event, like a car crash or something like that, where it gets deformed catastrophically, okay? So just be clear on that. Yeah, and fluids, gases, or liquids, we don't really look at that in particular in this area. If it is, it's probably the effect of gas or liquid in that it applies a hydrostatic pressure, or it applies a gas pressure, yeah? So due to the weight of the fluid or due to the pressure exerted by expansion of the gas. Here's a general, I guess, definition of it. Mechanics is an applied science closely related to physics. So many of the concepts we build on are that from physics. So this is the very reason why you guys do PH 102. It's an acknowledgement of physics. But from now on, we're looking at the application of those physics principles here in engineering, right? So physics is the foundation for engineering as well as mathematics, right? So, and then it goes on, mechanics is the foundation of many engineering topics and is an indispensable prerequisite for their study. I would suggest, and I'm very biased because I am a stress engineer, that it's the most important. Mechanics is the most important. But you'll run into some other lecturers here that'll say, oh, you know, manufacturing is the most important, or materials are the most important, or thermofluids are the most important. Can I just tell you, especially since this lecture is not being recorded, they're all lying, okay? It's mechanics. Mechanics is the most important. I'm just kidding, man. It isn't being recorded, right? Make sure it's not recorded. Tell me if it is. As soon as it is, I'm saying the other things, man.
It's not being recorded, sir.
I'm just joking anyway. I don't care if it's being recorded. Mechanics all the way. let's move on. Let's move on. How do I move on? Okay, here we go. So systems of units. Let me just expose all the slides so I know what it's talking about. Okay. So here we go. We've got kinetic units, length, time, mass, and force. That's okay. The first three of the kinetic units referred to as the basic units, maybe defined arbitrarily. The fourth unit referred to as a derived unit. Okay, must have a definition compatible with Newton's second law. So in this case, what we're saying is when we multiply these two together, kilograms and meters per second squared, what is our final unit? It's newtons. Okay, but it must be compatible. You can't go and say, you know, mass divided by area, right? Mass divided by area is pressure. You can't say mass divided by area is newtons, right? It's not right. It's pascals, right? If if the units are in kilograms and millimeters, it's going to be megapascals, right? So you've got to be consistent with your units. This is one thing I've noticed in teaching MM211 in first semester is you guys really need to get a hold and really be confident with your units. Now, to the point where if you guys can get in the habit now of conducting all of your equations, let me just see if I can annotate this. If I can just annotate this. Okay, so this here is really important. You may, and this is what happens is you get very confident with your calculation abilities and you start to leave the units off. You start to leave these units off, right? So then you end up with force equals 1 times 1 equals 1 Pascal. And it's like, well, wait, well, what happened? Well, you know that kilograms times meters per second squared is not pascals, but because you left the units off your calculation, okay, you end up forgetting what your units are. And in actual fact, it can be very handy when you're doing. So a very common equation that we would use in aerospace is coefficient of lift equals lift over half rho v squared s, where this is the lift force acting on the aircraft, this is density, this is velocity squared, and this is the planform area of our aircraft, yeah? Now, at the end of this, if you're not careful, you should have no units. This should be unitless because this is a coefficient, and by definition, coefficients are unitless. But if you were careful to put out here in newtons, and you'd put here kilograms per cubic meter, and this is meters per second, and that's all cubed, and then this is meters squared, you'd find the units all drop off. Okay? Now, that's the good thing about putting your units into your equations. Does that make sense, guys? I would suggest that's the takeaway from this slide is making sure that you carry your units through your calculations, at least at this very early stage. I'm considering you guys as baby engineers. You guys are baby engineers, and you'll grow into eating solid food later on, but some of you are skipping through to the solid food and you're forgetting the very basics of mathematics and engineering concepts. Okay, so I'm just really trying to highlight this because when you start to do some more complicated calculations, it really shows your knowledge of the field if you get the units incorrect of your final solution. Okay, now there's some really interesting ones, and I'll highlight. And this is I said that we would talk a little bit about Excel at some stage, especially with your lab stuff. But I'll just open up an Excel workbook here. Now, actually, before I do that, how many of you have access to Excel? Got thumbs up? You guys got access to Excel? I can see thumbs going up here in this room. I can see some going up here. Okay, I'm just scanning through. It looks like a lot of you have got access to Excel. Great, great, great. Now, if you don't have access to Excel, don't freak out. You can get free access pretty easily. You set up an account in a Microsoft Office account, yeah, an Outlook account. And when you set up an Outlook account, you get the best thing ever. Okay, the best thing ever is you have access to OneDrive. So let me just, you get a OneDrive account, okay? And OneDrive account is great. You get free 5 gigs, yeah? You get 5 gigabytes worth of free cloud storage, and you go, oh, I can get 20 gig or 15 gig on Google Drive. Google Drive sucks though, okay? Google Drive sucks because it doesn't have the Microsoft suite of software that you can use with it, okay? It does have its own kind of Excel clone and Word kind of processing clone, but OneDrive every day of the week, okay? And the great thing about it is you can sync it to your computer. So I have my OneDrive account, I have a pro account, and it's synced to my computer. So everything I save here is accessible to my PC at work. It's accessible on my phone because I can access the OneDrive account. And then I can open it anywhere as long as I have my cloud, as long as I've got access to the internet. And then I can open up Excel and I can use it on the cloud, okay? It doesn't have all the features. Well, I mean, Nicole, you can buy it or not buy it. It's free of charge, yeah? It's a very good tool though, okay? And it's much more intuitive than the Google stuff, okay? And all the Apple stuff. So I've got an Apple computer as well, and it's, you know, numbers and the document stuff is kind of, it doesn't mix well with, it doesn't play well with other applications, yeah? So I think the best thing for you to do is, if you don't have access to Excel, don't freak out. Just get access through Outlook account, okay? So that's my little promotion. Again, I get no money from this, but hopefully you'll learn something. So this is your Excel interface, okay? When you open up Excel, well, I'll just open up Excel, I guess. When you start with a new document, you get a blank workbook, okay? Now, again, if you've heard this before, great. If you haven't, welcome, okay? At the bottom, you'll get different tabs, and for some reason, my tab is not disappearing. It's not auto hiding. It should be auto hiding. Let me just make this up here. So you guys can see my screen, my Excel workbook. Yeah. Okay, hopefully. Excellent, excellent. So the first function that I want, you'll be able to see functions here, okay? Now, if you click on the insert function tab, you'll see all of the functions that are available to you. Now, here I've got a drop-down menu that says most recently used. You can switch to all, okay? You can switch to lookup and reference, statistical functions, date and time, math and trig. There's so many different ones, engineering ones here. These are all self-contained internal functions within Excel, okay? The one that I want to show you today is called the convert function. So the way you activate, yes, Nicole.
So you're going too fast.
No worries. So here, right, if you click, if you've got Excel up and going, you'll be able to see the insert function icon just above the equation bar, yeah? So when you click on that, you'll have this GUI that pops up, the insert function GUI. Over here in the drop-down tab, you'll see a whole bunch of categories, yeah? And you can select all of these categories. I often use the logical category. I also use the statistical one. math and trig, date and time. I use a lot of these. Lookup and reference is a really good one as well. For the purposes of this course, I don't think you'll require too many of these. You'll just require the ability to Rohan, man. I'm gonna like this guy, Rohan. I can't wait to meet Rohan. He'll be late to this meeting. He'll be late to our first meeting, I can guess. So in this one, I'm going to be using the convert function, okay? So convert is a function which allows you to convert different units, okay? So I've got it used, if you can see the tab that I've got right now. So I started off with this tab. When you create a tab, you'll see it just creates a sheet, and you can keep on creating as many tabs as you want, okay? And you can relabel these tabs. So you can right click on a tab and you can rename it. You can call it Nicole's tab, okay? Or Rohan is always late tab, yeah? Or you can have test questions or whatever. You can name them as many tabs as you want. You can also right click, and I think you can yeah, you can add a color to it. I always love putting colors into my Excel spreadsheets, just to highlight the different colors that you can have, and it just highlights the tab for specific purposes. Okay, so this is one way to do it. And also, typically when we're doing a stress analysis task, we would have different checks in different tabs. So we would have an axial check in one, we could have a bolt check in another one, we could have a stress, a bending stress check in another tab, so on and so forth, okay? Now in this one, I've got, this tab is conversions, okay? So we want to learn how to convert certain units. Now, we can always go and do other things too. We can go and figure out the conversion for ourselves, right? So we know that, for instance, we know 1 foot is equal to how many inches? You can put it in the chat if you have an idea. Yep, 12 inches. Great. And then we know 1 inch is equal to how many centimeters? Yep, 2.54. But I don't like working in centimeters. I like working in millimeters. So it's 25.4 millimeters. So technically, if we wanted to, we could jump from 1 foot through to 25.4 millimeters, or well, into millimeters, right? Using these conversions, right? Because we know 1 inch is 25.4 millimeters. We know there's 12 inches in a foot. So we can enter in whatever feet we have, multiply that by 12, multiply that by 25.4. Dwayne, change the colors. Oh my gosh, you're still back there. Just right click here, mate, and go tab color, see? And then you can change whatever Dwayne needs to concentrate. Tab. Okay. There we go. So there's a lot to learn in Excel. Okay. And let me just say, it's a journey. It's a journey. And I can teach you a lot in Excel. But we're not going to get everywhere today. Okay. So let's just go back to our conversion tab. So if we wanted to, I could have a conversion of, I want to convert feet, anything I put in feet into millimeters, right? So it would be, to activate the function in Excel, I click on equals. Can you all see that?
Yes, sir.
Okay, great. Equals starts an equation in Excel. So equals, and then I activate it by clicking on cells. So 1 foot, I need to multiply my feet. And then I click on the times. Times is shift 8. Yeah, it's the star. What do we call that? Star or, yeah, I'm pretty sure it's the star. And then remember, I need to go from feet, and then I need to go, yeah, asterisk, excellent, S111 7 4444. You might want to change your name, mate. So it's feet, then multiplied by inches, then multiplied by 25.4. Now that converts whatever I have in feet into millimeters, correct? So then I type enter. So 1 foot is equal to 304.8 millimeters. Yeah. So now if I change it to 3 feet, I automatically updates to 914.4 millimeters. Or if it's, you know, I'm 5'11". So that would be an interesting one. That would be equals to 5 plus bracket 11 divided by 12. Yeah. Which is 1,803.4 millimeters or 180 centimeters. Yeah. So that's my height in millimeters. You need to make sure that 5'11" gets placed into feet in the right, as a fraction. Yeah. Interestingly enough, there's other things you can do, and I'm probably going down a rabbit hole, but you can right click on this and come down to format cells. And in the format cells, you can actually format it as a fraction. Actually, I need to right click, format cells. Okay, and then I can display it as a fraction. Yeah. So there's different things you can do, but notice that typically when I go into Excel, I also color code my cells. Okay? So usually an input cell is yellow for me, an output cell is blue. So that way I know what in an Excel workbook or in a spreadsheet is where I need to input a number. Okay, the rest are reference cells, and typically I would use green. So if you ever came into one of my spreadsheets, you go, oh yeah, the yellow cell, that's the one that I need to enter a number in. Okay, now you'll notice, are you guys all still with me at this stage? Are you still with me?
Yes, sir.
Yeah. Nicole, have I slowed down enough?
Yes, you're all right, sir.
Okay, for now, so you can see I've gone from feet to millimeters here. The other thing that I can do is I can use the convert function. The convert function. So if you can look up here, I'll just drag this calculation over to the middle so you can all see it. So in this case, my input is my feet, my output is millimeters. So that's where I enter in a number. My conversion is here. So this is an inbuilt function within Excel. It's called upon using the convert syntax. So I put in equals, then I type in convert, and then I open brackets, and then you can see the format of this function. It requires a number, and then it's the starting unit, the base unit, and it's the convert to unit. Okay, so I'm converting from, in this case, feet to millimeters. And you can see the syntax that I use here. The feet needs to be within inverted commas. The millimeters needs to be within inverted commas. Okay. So if I'm doing this for the first time, I would come in here and I go equals, convert, open bracket. I need to convert what number? The number is 5'11". I can select whatever cell I want, 5'11", and I'm converting it from feet to millimeters. You'll notice that it also comes up in the drop down tab as well. So if you go equals convert, and then I enter in my number 5'11", it'll come up here. So you can scan down, and this has common ones, and it always annoys me, but typically, if you know what you're looking for, so I can see feet squared, and it might, I can't locate it, so I'm just going to type feet, but if you wanted to, if you could find it, you just double click there. Yeah? So it's feet, and then I'm converting it to millimeters. And then you type enter. So you can see what I managed to do here in column C is done very quickly in column F using the convert function. Okay. It's always handy for you to run through what I did in column C for yourself, and then you can have a check using a convert function, or you can even just use Google just to double check, right? So if you go to Google, I'm not sharing what I'm showing, am I? So if I share with you my web browser, so in Google, you can say, what's that? 5'11" in millimeters, yeah? Just type that in there. There you go, 1,803.4 millimeters. Okay, so that's a quick way to double check whether you've got the right conversion right. Okay. So that's just a little taste of what Excel is capable of, and just making sure that you guys have consistent units whenever you're doing this. Okay. The next slide, what do we have? Okay, this is kind of important, and I'll probably finish off on this, and I might start on this in our next lecture. Okay, but there are four steps in solving a problem. Okay, and these are the 4 steps that I want you to apply within this course and within every subsequent course. Yeah, thumbs up. We all good? Okay, make sure that we've got this one straight. The first step, number 1. Okay, strategy. Yep, awesome. Thanks. The number 1 is strategy. Okay, you should include a clear statement. You might summarize the problem that you've got in front of you, and then you need to decide what concepts apply to this problem. Okay, is it a statics problem? Is it a dynamic problem? Is it one that requires vector summation? Is it proportionality, or is it sine rule? What method are you going to use to solve this? Okay, but it starts off with you being able to present what do you understand by the problem? Exactly, Nicole, it's a problem statement, but what do you understand about the problem that's been presented in front of you? Okay, now the next one I believe is the most important one. Create a separate diagram for each body showing all quantities involved. In equilibrium analysis, clearly indicate all forces acting on each body, such as sketches, and in this case, a free body diagram. Okay. Now, it's not always the case in every problem that we have in this that we have a free body diagram, but it is very typically the case. Okay. So you need to basically distill reality into something that can be easily analyzed. Okay. And a lot of the times this will help clarify how you're going to solve this problem. It'll also help dictate what you know and what you don't know about this problem. Okay. So typically, typically in the strategy, I would write down, if I've got a particular problem, I would say, what do I know? I know the mass, I know the distance S of a certain situation, I know moment arms, I know this force, force 1, you know, so on and so forth. I would write down all the things that I know about the problem. Okay. Then I come into modeling, and I've got my free body diagram. That is typically what I do. Now, what does my free body diagram look like? Okay, so let me just go over to the whiteboard. I've still got it here. Okay, what does my free body diagram look like? So I did have something that I wanted to show afterwards, but anyway, let's just go with a free body diagram. It has these features. It has an axis system. Typically, it's my right hand rule. Everyone's got a right hand. You can hold your right hand up in front of you like this. This is my right hand rule, okay? Well, not my right hand rule, but your thumb is your x-axis. Your index finger is your y-axis, and your middle finger is the z-axis, okay? So if I go up here, this is your thumb. This is your index, okay? And coming out of the page is your z-axis, and that is your root finger, okay? But you guys don't know what that is. You're so innocent, right? It's your middle finger, yeah? Is it right or left? What do you mean? Praveet, it's the right-hand rule, my friend. Right-hand rule. It's always been the right-hand rule. Not the left-hand rule, mate. It doesn't matter. It doesn't care whether you're a lefty or a righty. It's right-hand rule, okay? Stop confusing all the students here, Praveet. The thumb is confusing you? Just get your thumb out, hold it up to the screen. You'll see on your right hand, your thumb is in the x-axis, your index finger is in the y-axis, your Z is coming out of the page. That's your root finger, okay? That's what it will have. Now, it will not have, it will be a free body. So if you're drawing a bridge, for example, you might have a truss structure. It does not have the supports in there. Instead, it has the reaction forces which represent the supports. Okay, so it might have RA, RAY, RAX, RB, and then you might have some applied forces, FI, yeah, for example. You will also have dimensions. Okay, so you might have 10 meters, 10 meters, 5 meters. Okay, you'll have dimensions on there as well. Now, everything that you have in a free body diagram should be able to allow you to perform the calculations. Okay, now obviously there might be some things that you might have to work out. You may need to work out some internal angles. You might have to work out some of these internal angles in order for you to perform calculations. You can always work them out to the side. But this is typically what would appear for your free body diagram, okay? Now remember, I love free body diagrams. It's a form of communication. It's you telling me that you understand what I'm asking you to do, okay? Don't skip these kinds of steps. They're very important, guys, okay? So let me just go back here. So analysis, the 6 fundamental principles applied to express the conditions of rest or motion of each body, the rules of algebra. So what are the 6 fundamental principles? There's 6 equations that we have for static bodies. Okay, there are our equilibrium equations. We have 6 of them. It's some of the forces in the X, Y, Z direction, and some of the moments about the X, Y, and Z axes. Yeah. So typically, when we're talking about the 6 fundamentals, we're talking about sum of the forces must equal 0, sum of the moments must equal 0. And they're about the X, Y, and Z axes. So that's why we have 6, yeah? You've got to take care of all 6 axes. Some of the forces in the X direction must equal 0. Some of the forces in the Y direction must equal 0. Some of the forces in the Z direction must equal 0. That is for equilibrium, okay? And then for equilibrium about rotational axes, some of the moments about the X axis must be equal to 0. Some of the forces, moments about the Y axis must be equal to 0. Some of the moments about the Z axis must be equal to 0. Okay. Then the final step in this, and we'll cover that as well later on. Okay, this is not the first and last time we ever talk about free body diagrams, strategies, and analysis. Okay, I'm just introducing it here for the first time. So don't feel like, oh my gosh, he's going so quickly. And most of you should have already covered this stuff in high school physics. Yeah. Then we've got rethink, reflect, and rethink. Test for errors. This is so important. Test for errors by verifying that the units of the computed results are correct. You need to test for errors, guys. Some of you are just following through with calculations and you're not thinking about whether the magnitude is correct. Sometimes you are orders of magnitude out and you don't even realize it, okay? Sometimes your distances, like you've got an answer that is clearly in millimeters and then you write meters as the final units. Now that's just requires you to put a bit of common sense and thought into it and realize what units are you in. Now for this, I want to propose to you this. You're my first year students. I love you dearly. I don't want to get angry at you later on because you mess up with your units, but I want you to be consistent with your units, okay? These are the units that I have worked with for 21 years. Newtons, millimeters, megapascals, okay? If you stick with newtons and millimeters, your answer will always be in megapascals. If you start with megapascals and millimeters, your force will come out in newtons. If you start with newtons and megapascals, your dimensions will come out in millimeters. That is consistent units. I could tell you another set of consistent units, which are newtons, meters, and pascals. You can do that as well, okay? But I want you to be consistent all the time. And typically, millimeters is the engineering dimension that we would use, okay? Mass is kilograms. Kilograms, not tons or anything like that. It'll be kilograms, okay? No worries. So, yeah, test for errors, test by substituting given data and computed results onto previously unused equations. This is why, guys, I would also advocate, I know you're in first year, but this is why I would also advocate you using Excel as a tool to verify your hand calculations. So when I worked at Boeing, we would consider hand calculations as being Excel calculations. We would perform all of our hand calculations within Excel. Now, obviously, we're in a test environment. You need to do your assignments and everything like that. So you would submit your things by hand. But you know what's a good thing to do is while you're doing it, when you're doing it at home, perform your calculation in Excel, okay? Make sure you muck around with the numbers and the units and stuff in Excel. It's very easy for you to change a number in Excel or a unit in Excel. You don't have to worry about rubbing out or crossing things off on a piece of paper. And then when you've got it right, translate what you've done on your Excel sheet onto a piece of paper that you could submit, yeah? Exactly, Rohan. Cross-check on Excel. Use that as some way of quickly double-checking your hand calc. Okay, so use the tools that you have in front of you, and always apply experience and physical intuition to assess whether the results seem reasonable. Test whether you believe the direction of a displacement is correct or whether the final resultant force is as you expected. Don't just trust that, oh, look, this is right. And you think, remember, you know, my wife always says, junk in, junk out, right? So whatever's coming in, if you put if you put rubbish into your Excel spreadsheet, rubbish is going to come out of it, okay? Those things don't change. So just make sure you're very careful with how you perform your calculations, yeah? And then lastly, we've got numerical accuracy. So typically when you're performing a calculation, whatever the accuracy of the data that's been given, if it's been given to 1 decimal place or 2 decimal places, your solution should be to that same level of accuracy, right? And that's what I usually do with my calculations as well. So typically gravity is to 2 decimal places, 9.81. So you might have your accuracy of your solution to 2 decimal places. So here we've got accuracy of the given data depends, or the solution depends on the accuracy of the given data, and 2, the accuracy of the computations performed. The solution cannot be more accurate or less accurate than these 2. Okay, and I would always apply that. Sometimes I saw in last semester in MM211, some people are going to 5, 6 decimal places. And unfortunately, this is a big problem. And what I'd like you to do, and I'd like you to think about when you're doing your calculations right at this stage is, don't extend your calculations to decimals. If you can avoid using decimals in your calculations, it's a good thing. So what I mean by that is, what do I mean by that? You can convert 2/3. Oh no, I've done it again. Let me just erase that. Actually, a better example is if I use square roots, right? So I can use square root of 2, or I can use, what's the square root of 2? I think it's 1.44. Yeah? What is that? I always forget these kinds of things. Okay, yeah, that's right, that's right. Okay. Thanks for, I need to just go back to my screen share. Where is it? Okay. Clear everything. Stop share. Sorry, I'm just going back. Okay. So you could use square root of 2 equals 1.414 each time, right? Or you can just keep it as root 2 and carry root 2 throughout your entire calculations. Now, this is in particular where you have, oh no, that's really bad. Typically where, that's even worse. Anyway, so that's 2, 1, 1, 2, and that's root 3. So this is 60 degrees here, this is 30 degrees. I always use this triangle when I'm using sine and cos of an equilateral triangle, right? So you can draw up this equation, so you can see sine of 60 is going to be equal to root 3 on 2. Sine of 30 is equal to a half. Cos of 30 is equal to root 3 on 2. Now you can take root 3 on 2 and change it into 0.866. Now you're gonna, if you do that, you're gonna lose some accuracy in your final solution. There's gonna be error that you introduce by dependent on the number of decimal places that you carry through your calculation. Now, because you guys want to remain accurate, some of you will carry 6 or 7 decimal places. Now, this adds more challenges in remaining accurate, and it takes time for you to punch in all of those decimal places, right, when you're performing your calculation. So my advice to you is get in the habit from now on of just carrying your fractions and your square roots through as a square root and as a fraction, okay? And that avoids having errors at the end of your calculation, okay? I think that is it. We're nearly at 9 o'clock. That's all I really wanted to cover today. I think we went through those 4 points that we started on. Okay, yeah, we covered what is mechanics, systems of units, methods of solving problems, and numerical accuracy. So I think I achieved what I wanted to achieve. Do we have any questions, guys? Guys and girls? Yeah, Nicole.
Sir, for revision wise, do you prefer us just revising the slides that you gave, or should we look over the textbooks that's prescribed?
Well, definitely, you can go through that. I don't think there's any questions really that I want. The next chapter that we go, there'll be questions that we can cover and we can do them in class. And we'll go through the tutorials. This one here is generally principles, yeah?
Okay, thank you.
No worries. Tukai.
Sir, could you explain in your own words what is an intuition?
Oh, well, intuition really depends on the experience that you have as an engineer. At this stage, your level of intuition may not be fully developed, but it's basically, it's I guess, a gathered experience which says, hey, this is right or this is wrong. When we're at Boeing, I would always call it the sniff test. Does it smell right? Does it look right? So your intuition, yeah, exactly, Pradeep, your gut feeling, I guess. Does that sit well with you? You know, is that number that you're getting, does that make sense? Or does it look wrong? Does something look wrong there? Now, if you're very new to something for the first time, you're not going to have very good intuition. You're not going to have a good gut feeling. Your instincts are going to be off. And so you may be led astray, and you need to develop that as you continue to do more calculation work, more analysis work. That'll develop further, okay? But at this stage, my suggestion is the more work you do on this, the better you'll get at it, okay? So for instance, if you get an answer that says 1 million megapascals, that is really big, okay? And you would question whether, hey, that doesn't sit right with me. If I get a force or an equivalent mass that is in the megatons, I'd be going, oh, I think I've done something wrong here. Or if I get a dimension that ends up being 0.000001 millimeters, I'd go, hey, this doesn't look right, okay? So you're expecting your number come out in an order of magnitude that makes sense to you, okay? And when those things don't come out, I would always ask you to question that. And that's why it's very important to go back and have a look at your checks and make sure what you're expecting comes through, right? So you might look at a particular problem and you go, hey, I'm expecting the resultant force to go in this direction. And when it doesn't go in that direction, you should question, hey, have I got it right? So maybe your interpretation was wrong, or your instincts were wrong, or maybe you've done something wrong in your calculation. Yeah. So I think that's what needs to happen. Nitesh, that's a very good question. I am going to cancel tomorrow's lecture. Okay, everybody. I'm going to cancel tomorrow's lecture because we're going to start to do some examples, and I don't think we're gonna have a good. Yeah, we won't be able to record it. Okay, and I want to record it so you can go back and have a look at it. And I wish today's lecture was recorded as well. I'm disappointed that it's not. But hey, let's stop it now. Yeah, let's not record. Let's not be here tomorrow. I don't want to waste your time, especially if you can't review the lecture again. And so let's regather next Tuesday. Okay, is it Tuesday, 8 a.m.?
Yes, sir.
Okay. Wait, there's a lot of questions coming through, and Yeah, sorry, Nitesh, I answered your question. Varaya, no, I won't be your lecturer for the entire course. I'll be taking the first 4 weeks, so I finish in week 4. Okay, so we got next week, another 3 weeks after that. Okay. Oh yeah, thanks SN for answering that. Okay, so what's this? Well, the OPP again, Mr. Jay Gounder he's the coordinator for the course, so I think the OPP has been sent and that should be distributed. Okay, but I think most of the lecture material is there, and then usually I come up with my own kind of problems. Well, I get them from the textbook, and then we'll cover those kind of example problems during tutorials, and also during lectures. I usually like to throw in a few examples at the end of the lecture. Okay. We're actually, hey guys, in actual fact, we're working, the university is working on a licensing system where you guys can get access to the textbooks online. And we were hoping we could get that through this semester. I'm really excited about it because I really want you guys to have textbooks. I know a lot of you are not purchasing textbooks. Right now, it's very hard for us to bring textbooks in, especially with the way the world is right now. But online, my advice is if your parents or you guys have a way of purchasing online, purchase the McGraw-Hill textbook online. It's really useful to have. And I lent out a lot of my textbooks to students last semester in 211. So I've got none that I can lend out to you. But whenever I purchase a textbook, I hold on to it. I don't let go of it. I think it's an invaluable resource that you'll carry with you for the rest of your engineering career. Nicole, you had your hand up?
Someone already said it. There's a site that you can download textbooks for free. It's called Z Library.
Yeah, but I would not know any of that, would I? It's good if you can get a hold of it. It's good that you can get a hold of it because a lot of the sample problems are in there. But obviously I'm not going to burn book publishers, right? They've put a lot of hard work into it. I would always advocate that you purchase the original product if you can. Again, it's something that you'll have for the rest of your life. And you got to invest in these things, yeah? Otherwise, eventually these book prices go up and up and up. And Chanel, so I'm not good at Excel and I might not conversion part we did. So later on, we might get a recap of that and some input. Well, yeah, Chanel, to be honest, Excel is very complicated. Yeah, I mean, complicated in the sense there's a lot to be done in Excel. If you want, yeah, I can do some of that. So will there be past sessions uploaded on Moodle past year? Like I said, I didn't do it. I'm not sure whether they're available online. I haven't checked the Moodle shell, so you can always check that. Praveet, we can download from the Z Library. Are you German, Praveet? We can download from the library. It's available there. Okay, great. So if you can get the textbook, is it? Praveet, is that what you're talking about? Yeah, no, I can't legally endorse downloading illegal stuff, guys. Yeah. But hey, everyone kind of did it, and luckily this session is not being recorded. But everyone did it when we were at university. We tried to get a hold of photocopied. I mean, you know, back when I was doing undergrad at Sydney University, there was a rule that you cannot photocopy more than 10% of a textbook. So you know, we'd all go in and photocopy 10%, and then we'd put it all together, and hey, we've got a full textbook. And that's what we used to do at the library. Here are the textbook. Is I think it's Mechanics of Statics or something like that, but go and check it out. It's in the course outline. Okay, it was covered in our very first lecture with Jay. I think it's written by Beer and Johnson, so it's a good book. You can find that in the course outline. Yes, Mosese, piracy. Yeah, minds of engineers, exactly. That's what we used to do, you know. I mean, you're no different, I guess. Thanks, Sean. Thanks for posting that there. Good stuff. Did someone want? Who was it? Was it who wanted me to do more Excel? Was that Chanel? Chanel? Well, I can open up Excel again if you want me to do it again.
Yes, sir.
So